So here we have number 6, which is where they want us to balance a redox reaction in acidic conditions. So our first step is to figure out what's being oxidized and what's being reduced by assigning oxidation numbers. So we'll start with this N2O2. We'll give the oxygens -2. Overall, we have -4. So the nitrogens must contribute +4, and they'll be +2. Okay, and then we have the ClO4-. So each oxygen's -2. Overall, they'd be contributing -8. So the chlorines must be +7 to maintain this -1 charge. We have our NO3-, so we'll give the oxygen -2, overall -6. Nitrogen needs to be +5 to make that -1 charge. We have our ClO2, so we'll do oxygen -2, overall -4. Chlorine's going to be +4. Done. Okay, so now we can see that the nitrogens changed oxidation number, going from +2 to +5. So it's becoming more positive, so it must be losing electrons. So it's being oxidized. And we can see the chlorine is changing its oxidation number. It's going from +7 to +4. It's going down, so it must be gaining electrons and being reduced. So now that we know that, we're going to split our reaction into half reactions. So we can start with our reduction half reaction, where we'll have ClO4- becoming ClO2. And then we can write our oxidation half reaction, which will be N2O2 becoming NO3-. So our first step is to balance our atoms. Make sure we have the same number of atoms that aren't oxygen or hydrogen, because those we'll take care of in a different way. So our chlorines are good in the first reaction, but here we can see our nitrogens are not balanced. So we'll have to put a 2 in front of the NO3-. Okay. So if we look at our original reaction, we can see that each nitrogen changed its oxidation state by 3. So we'll say each nitrogen lost 3 electrons. And in our reaction we have 2 nitrogens down in our half reaction. So we'll say that 6 electrons must have been lost. And then for the chlorines, the oxidation number also changed by 3. So we can say each chlorine gained 3 electrons. So then we can add a 3 here. Okay, so now we've taken care of electrons and our atoms. Now we have to think about our oxygens and our hydrogens. So if we look at our top reaction, we have 4 oxygens on the left, 2 on the right. So what we'll do is we'll add 2 waters to the right. So now they have the same number of oxygens, but we've introduced hydrogens now. So to take care of that, we'll have to add 4 protons to the left. And so I think that half reaction is balanced. And one way we can check is to make sure that the overall charge on the left is the same as the overall charge on the right. So here we have +4, -3, -1. So this side's overall neutral. And then on the right, we're overall neutral. So that seems good. Okay, now we'll have to do our oxygens and hydrogens on the bottom. So we can see on the left we have 2 oxygens, but on the right we have 6 oxygens. So we're going to have to add 4 waters to this side. Okay, but now we have to deal with our hydrogens, so I'll add 8 protons over here. We can check to make sure that our charges are the same on both sides. So here we're overall neutral. On the right we have -2, -6, so overall -8, +8, so we're neutral on that side too. So both of these individual half reactions appear to be balanced. So now what we have to do is combine our 2 half reactions. And when we go ahead to combine, we want to make sure that our number of electrons are the same. And right now they're not. We don't want to have any electrons in our final overall reaction. So what we're going to have to do is multiply the top reaction by 2, so both will have an exchange of 6 electrons. And so once we've multiplied that reaction by 2, and we have the same number of electrons, we can go ahead and combine our 2 reactions to get some overall reaction. So now we have our overall reaction. But now we need to make sure that we simplify it down because we have water and protons on both sides of the equation. And so if we look at our protons here in orange, we're going to have to cancel some of them out. And it works out that we have the same amount on both sides, so we're just going to cancel them out. And when we look at our waters, we have the same number on both sides, so we're just going to cancel those out. And our final equation then would be just 2 of our ClO4 minuses with our N2O2, making 2 ClO2 and 2 NO3 minuses. So, it might be a very unsatisfying answer to do all this work and to get an answer of 0, but we really couldn't have settled on that answer without going through the whole long process. And if you're going through and you feel like you've made a mistake or something's not adding up, just stop, erase everything, and start over, because it can be really hard to go back and find errors because everything's sort of interlaced. Okay, so in number 7 we have a solution of zinc hydroxide, and they give us the concentration of zinc and the pH. So they want us to figure out the molar solubility of this if we had a pH instead of 11.5. So in this problem they don't give a KSP for the zinc hydroxide, so that's going to be my first step. I'm going to figure out what the KSP is using the first batch of information they've given me. So I know the KSP is going to be the zinc ions times the hydroxide ions squared divide by 1 because we have a solid. And so this first piece of information they give me is telling me about equilibrium zinc concentration and equilibrium hydroxide concentrations. So I can just go ahead and plug those concentrations in to solve for my KSP. So I'm going to have 5 times 10 to the negative 3 molar for my zinc times my hydroxide concentration. So if I have a pH of 7, I also have a pOH of 7. And so 10 to the power of my negative pOH will give me my concentration of hydroxide, and then that will be squared. And I find that the KSP is 5 times 10 to the negative 17. And so that is what we'll have to use when we're doing our ice table to figure out the molar solubility of zinc hydroxide in a different concentration of hydroxide solution. So that pH of 11.5 tells me I have a pOH equal to 2.5. And I can use that pOH as my hydroxide concentration, or to get my hydroxide concentration. So if I know my hydroxide concentration, I can solve for my zinc ion concentration using the KSP. So I'll solve for this and say that my KSP, which I found to be 5 times 10 to the negative 17, is equal to that zinc concentration that I'm wondering about, times my hydroxide concentration, which is 10 to the negative 2.5 molar, squared. And so I'm going to solve for the zinc concentration, which will serve as my molar solubility, which is 5 times 10 to the negative 12 molar. Okay, so the answer here is going to be B. In number 8, they're asking which metal could be used as a sacrificial anode to protect a piece of cobalt from corrosion. So we want to find something that's better at being oxidized than cobalt. And so we can look for their oxidation potentials on the data table by finding these metals on the product side of the reactions and flipping the potentials. So I'm going to write those in here. So if we're looking for something that would be better at being oxidized than cobalt, we want something that would have a more positive oxidation potential, and that will be iron. So iron would be the better sacrificial, or the best sacrificial anode to protect cobalt from corrosion. In question 9, they're asking us to figure out the KEQ for the given reaction given the KEQs for two other things. So give us the KSP for copper chloride. So I'm going to start by running the reaction for that, knowing that KSP always corresponds to taking a solid and breaking it into its aqueous ions. And they give us the KF for some complex. And I know that KF is formation, and it's bringing the individual components of the complex together. And then I can see, if I compare the two reactions that I've written to the one up here, I don't want there to be any copper ions, because there's none here. And as this is written now, we have copper ions on opposite sides of our two equations, so they would cancel, leaving us with the components that we do want. So all we have to do is add these two equations together, and we'll end up with that same equation that's written above. And so when we add two equations together, we know that we can multiply the KEQs. So our KEQ will just be our KF times our KSP, and we end up with a value that's 1.84 times 10 to the 5th. And that corresponds to answer choice B. So be sure you can write out the KSP and KF reactions given just one of the molecules in there. Okay, and number 10, they're asking which will result in a decrease in the solubility of manganese carbonate. So a decrease in solubility is going to correspond to a shift left in the reaction. We're going to go more towards solid and less toward the ions. Okay, so first we add in HNO3, which we know is a strong acid. So really what we're kind of adding in are protons. And so we have to say, will either of these things react with protons? And we know that the carbonate will react with protons to make carbonic acid. And so that's kind of pulling carbonate out of the reaction and sucking it into more of an acid-base equilibrium, removing it from here. And so adding that in and removing carbonate ions from this balance would lead to a shift to the right. And that would be increasing the solubility. So that one wouldn't be the answer. And for the same reason, E is not going to be the answer. Okay, and then in B, we know this is a strong electrolyte, so it's going to break into sodium ions and carbonate ions. And so the sodium's not involved in our equilibrium at all, but the carbonate is. So we'd be adding in more carbonate. If we're adding in more of a product, we're going to shift left toward reactants, which would be a decrease in our solubility. So B is the answer. And then both C and D won't affect the solubility. Okay,